So the first one, part A. Given this function, which is a simple product, obtain the values of x for which the derivative equals 0. Well, it's a product, so we just differentiate it straight away using the product rule. Differentiate the first one, that's just 1. Leave that alone. Now, leave the first one alone and differentiate that, which is a simple function of a function. So it'll be 3 times the inner function, power 2 times the derivative of the inner function, which is just 1. So that gives me x minus 2 cubed plus, and that's 3x plus 1 times x minus 2 squared. Right, factorise it. It's a pair of brackets, the same there. X minus 2, I can get 2 of them out, and that's going to leave me with x minus 2 and 3x plus 1. Tidy that up, squared, because that'll just be a linear term in there. I've got 3 and 1 more makes 4x minus 2, but plus 3 is plus 1. So f dash of x equals that. Right, that was the first part of that. And then the second part said, right, find the values of x for which the derivative equals 0. Well, f dash x equals 0 simply means that this already factorised expression here will equal 0, in which case x is either going to equal 2 or x is going to be negative a quarter. Or strictly speaking, there's a double root at 2 and a single root at x equals a quarter, but that's all it's asking for. Right, that's part A. Now part B, calculate the gradient to the curve defined by this expression. So part B, calculate the gradient of the curve defined by this implicit equation at the point, we'll put a wee note of that, 3, negative 1. So it's just going to be differentiated and then substitute in those values for x and y. Well, not want to do the quotient rule particularly, I think I'll just multiply everything by y. So I've got x squared plus xy is y squared minus 5y. Which is perfectly fair because y couldn't have been 0 in the first place, so that would have been undefined. Right, differentiating that. So it'll be 2x plus, now here's a wee product, 1 times y, and then x times dy by dx equals 2y, it's a function of a function, times dy by dx minus 5 times dy by dx. Right, gathering that lot up, probably need to have taken that to this side and then writing it over there. So I've got my 2y minus the x lots of it minus the 5 lots of it for dy by dx equals what's over that side, and what's over that side is a 2x plus a y. So dy by dx is going to be 2x plus y over 2y minus x minus 5. Right, that was the first bit. Then the second part is, what's the value of the gradient? Well, the gradient will be equal to that, which will be 2 times, started, so I'll have to carry on that way, plus negative 1 over 2 times negative 1 minus that 3 minus 5, so that's going to be 6, take away 1 is 5, over that lot comes the negative 10, so the gradient is going to be negative a half. Now, maybe you didn't end up with this expression. Have I got room to squeeze it down here? If you'd started off with this and left it and did it as the quotient rule, you'd have had this over y squared, then it would have been differentiate that, leave the bottom one alone, and then leave that alone, multiplied by the derivative of the bottom, dy by dx, plus 1 equals dy by dx, and that would be all. And then you'd multiply through it by the y squared. So you would have done this. That'll be plus y squared equals y squared dy by dx. That's getting a bit messy. Bring that over to join that, but write it over here. So y squared plus the x squared. So x squared plus y squared dy by dx would have equaled, reading that side, I've got 2xy plus y squared, which means dy by dx is 2xy plus y squared over x squared plus y squared. And then you look at these two expressions and think, how are they the same? And in truth, if you were just to try and do simple algebra to change one into the other, then that wouldn't happen. But the connection comes from the original equation. We'll take that one step further. If you work that out, you're still going to get the same answer if you put the numbers into that. They are actually the same because there's a connection between the x's and the y's. When you look at those and think, oh, they're different, that's because you're assuming that the x's and the y's are independent variables and I have to try and change one bit of algebra into another. No, they're connected by this. You could show they're the same simply by doing this part. I know it's not necessary for the question, it's just in case you've got that and you thought, how is that the same as that? Well, it is actually. Well, there's various ways you could change it by using these expressions. Well, you take the y out of that. If you take the y out of that, you've got 2x plus y over x squared plus y squared. Now there, I've got the top. So I've got 2x plus y, divide everything by y, over x squared over y plus y. X squared over y can be written as this. Have I got room here? 2x plus y, it's getting tight now. X squared over y is y minus x minus 5. Y minus x minus 5 plus another y. So I've got 2x plus y over 2y minus x minus 5. Same expression. Right, that was question 1. Question 2 then. Small matrix question. Small 2 by 2 square matrix. Matrix. Question 2. Small matrix question. You've got a 2 by 2 square matrix here and you defined its inverse when it's non-singular. Well, you could only do that if it was non-singular. So finding its inverse. Well, to find its inverse, you're actually going to use, although I'm probably not aware of it, you're going to use the adjugate of it. That's when you reverse the main diagonal terms and turn the other ones into their negatives. That's actually the result of using something called adjugate. And then divide by the determinant of it. So the first thing you do is you find its determinant. What's the determinant of A? Well, that would be t plus 4, 3t, 3, 5, which is simply the main diagonal. So that's going to be 5 times t plus 4 minus the other diagonal, 3 times 3t. So that's going to give you 5t plus 20 minus 9t, which is going to be 20 minus 4t, which will then give you the inverse of the matrix as 1 over 20 minus 4t times, and then this little arrangement that you've learnt, which is actually the adjugate, which is reverse the main diagonal and then put the other two into their negatives. Right, there's the first bit. Part B. Write down the value of t such that it's singular. Right, I'll just put a wee statement. A singular if the determinant 20 minus 4t equals 0. So that means 4t would have to equal 20, so t would have to equal 5. There's only one mark for that. For part C, given the transpose of A. Right, the transpose of A means to interchange the rows and columns. Make the first row into the first column, and make the second row into the second column, which is just the same as flipping it over the main diagonal. It says the transpose of A is equal to this thing, which means if the matrices are equal, all the entries must be the same, and they are. Look, 3, 3, 5, 5. So that means that t plus 4 must equal 6, and 3t must also equal 6, where they're both equivalent to saying t equals 2. For that mark. That was question 2. So question 3 then. Given this little first order differential equation, separable, find y in terms of x, given these two values to put in to take care of that little constant that will pop out of that integration. Right, well, separable. So, e to the y, you can stay with your friends there, and d to the x will go over, x squared underneath, then integrate both sides. So that means that will stay as e to the y. X to the negative 2 will go back up to x to the negative 1, so that's negative 1 over x, and here comes that constant. Substitute in as soon as it appears, rather than letting it snake its way into the various expressions. So as soon as it appears, it'd be this. What have I got? E to the 0 is going to be negative 1 over 1 plus c. Well, that's just 1. 1 equals negative 1 plus c, so c equals 2. So e to the y is negative 1 over x plus 2. Wish I'd written that as 2 minus 1 over x, but I'll do that in the next line. So to get y, inverse of the e will be ln. So ln of 2 minus 1 over x. Oh, that was a very easy little question. Question 4, a proof by induction. A summation one, only with fractions in it. Well, as before, the first thing you do is just check it's true at the start. It says it's true for all positive integers n. So you're considering n as any of the natural numbers n, those being the positive integers. Well, test it then. Test it for n equals 1. The simplest way is just to refer to that as the left-hand side, and that's the right-hand side. Well, if n was 1, the left-hand side would simply be the very first term, so there'd be no summation. It'd just be 1 over 1 plus 1, 1 over 2, that's a half. The right-hand side is 1 minus 1 over 1 plus 1, 1 minus a half, which is a half. So you can say the right-hand side equals the left-hand side. Don't know why I put it backwards, which means the important bit, it's true for n equals 1. Left-hand side equals the right-hand side, so it's true for n equals 1. Then, the inductive hypothesis. Assume it's true for some arbitrary position for n equals k. In other words, if you were to take the summation from r equals 1 to k of 1 over r plus 1, you would get 1 minus 1 over k plus 1. That's the inductive hypothesis. And then consider n equals k plus 1. Consider the next part after that. Well, k plus 1 means this. You've got sigma from r is 1 to k plus 1 of that thing, of that expression. Well, that simply means you've got this expression plus the next term. That would equal sigma r equals 1 to k. That's most of it. That's adding it all the way up to k of 1 over r plus 1, plus the next term, which would be this with k plus 1's in it. So that would be 1 over, now r would be the final value, k plus 1 times k plus 1 plus 1. Then calling in your inductive hypothesis, calling in 1, I'm saying that this part is equivalent to that. So I've got 1 minus 1 over k plus 1 plus this thing, where that's k plus 1, k plus 2, and I'll just put by 1 because I need to call that in. And now somehow I've got to make this rearrange back into this original form, only with that n is a k plus 1. Well, I want 1 minus, so I'm going to preserve that minus by putting a bracket in here. Then these two fractions, I'll put these two together. So I'm going to have, I've got a k plus 1 and I've got a k plus 2. That will need the k plus 2. I'm saying minus, so that'll have to go down as minus. And I've got all of that, so it's just minus 1. So it's 1 minus, and that's just k plus 1 then, over k plus 1, which had a bit more room, k plus 2. Can I just write it at the side here? So that's 1 minus, those parts cancelling, 1 over k plus 2. Almost there. Rewrite that as 1 minus 1 over, and k plus 2 can be reorganised as k plus 1 plus 1, which is precisely what the expression should be if n was k plus 1. So now I can say, but I've not exactly got enough room, which means if it was true for n equals k, then it's turned out to be true for n equals k plus 1, because I obtained the original expression with k plus 1. Hope this shows. And then, since since it was true for n equals 1, then by induction, because induction has shown that consecutive terms are true. If it's true at one term, then that's true for the next one. So if it's true at 1, it's true at 2, true at 2, true at 3. By induction, it must be true for all n, where n were the positive integers, where n were the natural numbers. Right, that was question 4. Number 5. This is a definite integral. Show that this comes to ln 9/5. Now there's two ways you could do that. You could do it by inspection, because you might notice that the top is the derivative of the bottom, in which case that simply integrates into ln of the denominator, and then evaluate it these two parts. But you probably didn't do it that way. You probably did a substitution. So I'll do the substitution first of all. So I'm guessing you'd probably have set it out like this. Let u, or whatever you chose, equal e to the x minus e to the negative x. So that du by dx was e to the x multiplied by that plus e to the negative x being the top. So that dx would have been du over e to the x plus e to the negative x. They'd have had to change their limits. So that when x equaled ln of 2, u would have equaled e to the ln of 2 minus e to the negative ln of 2. Now, e to the ln of 2 is just 2. The negative of the ln of 2 is equal to the ln of 2 to the negative 1 equals ln of a half. So that's 2 minus a half. 2 minus a half, so you've got 3 upon 2. Similarly, x equals ln 3 upon 2. Now all this work here is the majority of the work that would have done the other way if you'd used just inspection. That means u is going to be e to the ln 3 upon 2 minus e to the negative ln 3 upon 2. So that'll be 3 upon 2 minus, same principle, ln, negative the log of power negative 1, so that's just the reciprocal, minus 2/3. So I'll have to change that into sixths then. So that's going to give me 5/6. And then back over here again. So I've got it going from 5/6 to 3/2 of e to the x plus e to the negative x over, I've already changed that of course, over u times du over e to the x plus e to the negative x. Those two cancelling out. Do I need to write that down again? Oh, I'll do it anyway. From 5/6 to 3 upon 2 of du upon u. So that's simply going to be ln u from 5/6 to 3 upon 2. So that's going to be ln of 3 upon 2 minus ln of 5/6. Subtracting the logarithms, we'll be dividing them. So 3 upon 2 divided by that. So multiply by the reciprocal. That gives me ln of, cancels out, 3 3's 9, ln 9 upon 5 as required. I took an awful lot of work. Most of the work was actually in this bit. Now you could have just done it by inspection. So, by inspection, which means simply noticing the top is exactly the derivative of the bottom. So that's precisely the logarithm of the denominator. If you wanted to give a reason, you could put that down. You could say this, I'll put it down. So I'll say, since d by dx of e to the x minus e to the negative x equals e to the x plus e to the negative x, that means that that integral that I was going to evaluate is exactly equal to ln of e to the x minus e to the negative x, evaluated from ln 3 upon 2 to ln 2. And then substitute the figures in. So I've got ln of e to the ln2 minus e to the negative ln2 minus ln of, and these are all positives, e to the ln 3 upon 2 minus e to the negative ln 3 upon 2. So that's ln of, now that comes to 2. As before, the negative of ln2 is ln of 2 to the negative 1 is ln a half. So minus a half minus ln of, straightforwardly for this one, e to that is going to be 3 upon 2 minus ln negative of the log is a log of power negative 1, which is the reciprocal, minus 2 upon 3. So I've got ln of, you tidy it up just now, tidy it up afterwards, subtracting, so divide, maybe I'll just put it down differently this time, instead of doing the separate fractions, divided by 3 upon 2 minus 2/3, multiply everything by 6 to get rid of these fractions, so I'll have 12 minus 3 over 9 minus 4, which as before gives you 9 upon 5. For question 5. So question 6. Express this quotient of complex numbers in the form a plus ib, where a and b are real numbers, right? And then show z, show the number on an Argand diagram and get the modulus and argument. Fair enough. So what I'll have to do is I'll have to multiply out that bracket and then realise that denominator. So multiplying out the bracket, so it's square the first, twice the product, square the last, which will be minus 4, then multiply the top and the bottom by the conjugate of that, thus forming the pattern for what would normally be the difference of two squares, but in terms of the complex numbers is the pattern for the sum of two squares. So the bottom's quite easy, that's going to be 49 plus 1. But the top part I'll need to multiply that lot out. So for that I could have tidied it first, but I'll tidy it as I go because I know I've got a negative 3 there. So I've got negative 3 times that, so that's negative 21 minus 3i, and then plus 28i, and then minus 4 again for that part. So that means for the real part I'm going to have negative 25 and then plus 25i over 50. Well, that's all going down to a half then, isn't it? I've got a negative a half plus a half I for z. Then, show it in an Argand diagram. Well, fair enough. What's this called? Part A, part B. No, just express in that form and then show it. So, imaginary part, real part, just approximately. Oh, I was going to give me tiny numbers. Maybe I shouldn't put the scale in. So negative a half, I'll just say that's a half there. Negative a half, that's what z would be. If that's negative a half, and that's a half in terms of I. The modulus and the argument. The modulus means the length of that ray that goes from the origin to the point itself, and the argument means the angle round clockwise from the real axis, unless it exceeds the halfway point, in which case it's the angle the opposite way round. Well, so for the modulus of it, the modulus of z, I'll just put modulus of z squared, it's going to be the real part squared plus the imaginary part squared. So that's going to be a quarter plus a quarter is a half. So the modulus of z is going to be the square root of that. The square root of a half, which is either 1 upon root 2, or if you want, you can put that as a root 2 upon 2, if you prefer a rational denominator. I'll just leave that one. And then the angle, the argument. The argument of z is going to be the inverse tan of the distance up over distance along there, of the imaginary part portion over the real portion. That'd be negative. You recognise it immediately. That's going to come to -1. I'll put it down there. Inverse tan of -1. Now 1 would be 45 degrees, so I'll be 135. So put it down whichever way you like. 135 degrees, or, if you will, 3 pi upon 4. Yeah, that's question 6.